All right. Welcome back. So I will announce the official results of the vote at administrivia time. So if you remember from last time, we actually talked about queuing theory, and hopefully they talked about it in a section on Friday as well. But the key thing about the queuing theory, we talked about several key things. One, it's about the steady state, not transient states. So if you want to do something with transient queuing theory, that's a much more complicated topic that we don't make you responsible for. The second thing to note about queuing theory is it's pretty much going to give you some average behavior. It'll give you some way of analyzing how well your system works, but it's not going to give you exact results. So don't get confused about that. The three parameters of the queuing model we gave you are lambda t service time and c for the server. I suppose I should actually say this is c sub ser. And once you've got those three parameters, you're good to go. All right, so basically everything else is derived from those three parameters. So if you can figure out what these three things are in your system, then you're good. So the arrival rate is literally number of things coming in per unit time, and the assumption is that this is a memoryless distribution. Okay, and then the server has the other two parameters, which is the average time to do service, that's t ser, and then c, which is about how much standard deviation is there about the mean, where c is, of course, sigma squared over m1 squared. So this is the standard deviation squared, otherwise known as the variance divided by the mean squared. So if you can figure out what those three things are, then you just plug it into the equations we gave you last time, and we're good. And this was the most general equation we derived, which is the time in the queue is the service time times 1/2 1 plus c times then u over 1 minus u, and u is the utilization. Okay, and you notice that if c equal 1, namely memoryless, you go from here to here. Okay, so it's all about figuring out what your parameters are and then using the queuing model to figure out what the time in the queue is, and then from there you figure out the length of the queue by Little's law. That's just lambda times time in the queue, and you're good. Were there any questions on kind of the overall idea here? I mean, details about the derivation of the proof are things you could ask me about after hours, but in terms of, or office hours or something, but in terms of the overall what we're trying to get out of this queuing model, does that make sense to everybody? Yeah, question. Say again? So where you get c from, so the cutesy answer is it's, you find out what your standard deviation squared over your t ser squared is, and that would give you c. In reality, what you often say is you find out that you have a server that is behaves with c equal 1 or c equal 1/2 or c equals 0. So that's often given to you as a constraint on the server. And the two that you should really know well are c equals 0, which is what? What's c equals 0 mean? What is the standard deviation when c is 0? 0. So that's a deterministic time. Okay, so if your server always takes exactly t ser long, then c would be 0, and that's one extreme. Another is if the server is memoryless, then c equal 1. So those are two very good numbers of c to know right off the bat. And then if anything else, we would probably give you in a problem. Or in principle, if you were on your own, you'd calculate it by knowing something about what the standard deviation is. Okay, that answer that question? Good. Any other questions? So it looks messy, but there are only three parameters, and there's something very specific you're trying to compute, which is how long are you in the queue. Okay? And by the way, the time in the queue is different from the time to get service. So don't get confused. If you're actually asked, I come in the door at McDonald's and I want to know how long until I go out the door, that's t sub q plus t ser, because there's actually a service time for you, the person coming into McDonald's. Okay? All right. I'll let this go now unless there's any other questions. Are we good? It's all about, can you get those three parameters? Okay. And just so you know, When C equal 1, this is called an MM1 queue because it's memoryless input, memoryless output. If C is not 1, then it's called an MG1 queue, for that's a memoryless input general output. If you pick up a queuing theory book, you'll actually see a GG1 queue, and the mathematics are much messier there. But in principle, you can deal with any kind of input and any kind of output if you want. And then there are multiple queue versions and yada, yada, yada. OK. The other thing, just to get us back into disks, so we were talking about disk scheduling at the very end of the lecture before we started plowing into file systems. And if you remember, the problem here is that the disk has got a physical arm that's moving, which is slow relative to everything else. And so we want to optimize the movement of the arm. And so while we could take a series of requests coming in from different users, this is sort of representing track 2, sector 3, track 2, sector 1, so on and so forth, we could process those in first come, first serve order. And that would be fair in some weird definition of fair, but it certainly seems to be a waste of head movement because we're moving all over the place. And what we really want to do is somehow optimize so we don't move the head much. And that's where these different algorithms came in. And the one that's most important here is the scan algorithm, otherwise known as the elevator algorithm. And the idea there is that just like an elevator, the thing is that's scanning in and scanning out. And what you're doing is you're picking up all the requests on the way in and the way out, just like an elevator does. OK, and that's sort of trying to optimize or minimize the amount of head movement. OK, were there any questions on this? Good. And where did we say that the elevator algorithm is often done these days? Inside the disk, OK, or sitting out here in the hallway. OK. So today I want to talk about file systems. And we'll see how this may be overly optimistic, but I want to talk about a bunch of different file system issues and introduce you to some inode structures. And if we're lucky, we'll talk about caching and data durability. But we'll see where we go with that. OK? Oh, and somewhere in there, we'll talk about the midterm. So how do users access files? So in order to really optimize a file system, we want to talk about the access patterns. And we started talking about this last time, so that maybe our file system serves the users well. Okay? And clearly, sequential access is the one that everybody needs a lot these days, especially with multimedia. And that is, you start at byte 0, and then byte 1, then byte 2, and you kind of work your way from the beginning to the end of the file. And why do we want that? Well, videos, audio, pretty much any multimedia is referenced that way. Although when you think about it, how many of you have clicked to different parts of songs or whatever, right? Or clicked to different parts of video? There's clearly a random access component even in video players. It's just the most predominant pattern is the scan forward pattern, sequential. But this random access notion of being able to reach into a file at any point and continue, or reach into a file at any point and grab a chunk in the middle is very important. Okay, that's the ability to, well, for instance, go to the middle of a video, but also the ability to do databases or whatever. Okay, so as two very important patterns here, if our file system can't do either sequential access or random access, then we probably have a problem. The other thing I kind of mentioned, which a lot of file systems aren't optimizing for yet, is this notion of content-based access, where what I really do is I access the file by saying, here is an index to what I want, find it for me. Find all email messages that reference somebody or whatever. Okay? And that's kind of the Google desktop view, which is an app that you can actually download from Google and put on your system. And it does for your local drive what Google does for the internet as a whole. It basically lets you content search your disk. Okay? All right. So pushing on the usage pattern for a moment. So are files mostly small or mostly big? Well, it's kind of interesting. If you actually look, there's a few files that are really big, okay, sort of Nachos itself, core files, et cetera, maybe videos and movies. But there's also lots of small files. So when a lot of file systems were originally developed, people did this kind of distribution of file sizes. And they said, oh, look, by far and large, most of the files are little ones, but we better optimize well for big ones. Okay? And interestingly, of course, although there are not that many of them, the big files easily take up most of the disk space. Okay, so you've got a smaller number of files that take up most of the space. There's a whole new class of system, obviously, things like iPods, where most of what's on there are large files now, right? Video or audio. And that's kind of, that's a different type of file system maybe than the ones that we'll talk about today could be useful there. Although in most cases what's happened is people have just taken regular file systems and sort of adapted them to handling multimedia. So we could take this data and we could design the perfect file system for this data. What is the data? Well, you want to do sequential mostly. You want to do some random. Most of the files are small, but you have some really big ones that take the whole disk. And we might be spot on, but it's always interesting to be careful. And there's a couple of fun things here. It's maybe a good idea to look at usage patterns, because then you beat your competitor on some metric that you can brag about on an ad. But maybe the usage will change over time and you've over-optimized for a usage pattern. You've got to be careful about that. Maybe, for instance, Unix, which is where a lot of these file systems were originally designed, has mostly small files because big ones didn't work very well. Okay, so that could almost be a self-fulfilling prophecy. And there are other examples of people being completely wrong. Like I think at one point IBM did a key study and concluded that there would be a maximum of about 7 computers worldwide. Well, we know where that went, right? So you got to be a little bit careful about your data. So how do you organize files on the disk? So our goals are, 1, we want to maximize sequential performance. 2, we want to have easy random access. 3, we want to be able to manage files. So if they grow or they shrink or whatever, that's got to be possible. Okay, because you edit files all the time. So one option here, which is the simplest thing we could come up with, is continuous allocation. So what you do is you use a continuous range of blocks on the disk, and every file has to be a contiguous, non-broken block group of disk blocks. Okay? So this is kind of like, remember when we talked about segmented memory first time around, before we sort of put paging into it, we sort of talked about a base and a bounds in memory, and you could do this on disk, right? So what's the great thing about this? Well, it's got the best sequential performance you could imagine. Why? Because you park the head in one place and you let the disk spin and you got the whole file. Or at worst, maybe you have to step a little bit. Okay? A downside maybe is that the user actually has to say something about how big the file is before they open it. Why might that be true? Why do you have to say in advance how big the file is going to be before you open it? Yeah. If your file turns bigger than the base down or the down, then you have to move the rest of the file. Yeah, this is the ultimate fragmentation problem, right? Because if your file no longer fits, then you got a problem. You got to move it. Okay, so this seems like as simple as this technique might be, it's got some downside. You had a comment? Sure. So that's kind of the same thing here. We got to reserve space so that we're not overwriting our space we need. Yes. And now if you think about how you use files, right? You open and then you do write, close. Oftentimes the size of the file isn't even known until after you hit close. Okay, so this constraint doesn't work very well. Another aspect of this is, so how do we implement this? Well, we might have a bitmap of free space, and what we need to do is find the biggest chunk that sort of exactly fits what we want. So there's some algorithm there we'd have to come up with, but you're probably smart enough to figure that out. But if there's not enough contiguous space for what they ask for, then what do? You got to move stuff around, which is extraordinarily expensive. Okay? Anybody here defragmented their disk before? Isn't that fun? What's really fun is when you catch yourself watching it. Then you know you've been up too long, right? Oh, look. I've never done that, of course. So going on this technique here for a moment, what's a file header? Well, it's very simple, right? The file header just needs to know what the first sector or logical block address is in the file and how big it is, and that's all. So describing a file is really simple. Okay? So pros here, fast sequential access. Why is random access really easy in this architecture, this file system? Yeah. Yeah, you take your starting point, you add the offset, and you go right there on the disk, right? Because the disk is random access. So this file system supports random access pretty easily. Of course, all these cons are, fragmentation, hard to grow the files, the set of free holes on your disk, which you might try to optimize for in order to allow you to easily add new files. They get smaller over time, and then you finally end up moving space around. So, did anybody ever use this? Yes. This was actually in IBM 360, initially had this type of allocation for their file system. Okay, so it seems like it's inflexible, but yes, indeed, it was used. And the results, well, people would plan for the future by asking for a huge chunk of disk space and put it smack in the middle of the disk. Why? Well, because they wanted the potential to grow later. And so, I don't know how much I need now, so just give me this huge chunk. And as a result, you end up with all this wasted space of people claiming space they never end up using. Okay? All right. So this will clearly be the simplest file system we come up with. So does everybody catch how this works? Okay, so file system's got, a descriptor, a header that somehow points to what blocks are needed for the file. And this is particularly easy because it's got two numbers, a starting sector and a length. So I guarantee the rest of them are going to be more complicated, but more flexible. All right. So another option is we could link blocks together. So, our header here for the file is basically a pointer to the first block, and then each block has a pointer to the subsequent blocks until you hit the null pointer, and then you're done. Okay? So, the pros of this is you can easily grow the file dynamically. In fact, the free list could look exactly the same as a file. So the free list is just the huge file that has all the blocks that aren't used in it in a linked list. Okay? Cons, really, really bad sequential access. Okay, now, why? Why is this really bad sequential access? Yes? Yeah, there's nothing in this particular description that says there's any locality here. So this block could be on a completely different track from this one and so on. Now, let's make sure that we understand what I just said here. I didn't say that there is no way to have an efficient sequential access for a file with this organization. If you were lucky enough to be able to put a set of sequential blocks together, maybe the access is okay. Okay? But let me actually argue why even if you did a good job of allocating, so every block is on the same track, can somebody tell me why you might not actually get the full speed of pulling things off the disk even in that case? Yes? Yeah, so you got to read this block, find the pointer, and then act on it. And by the time you do that, the disk is rotated past the next block. Okay, so in order to really make this thing work well, you'd have to sort of alternate blocks and make sure you were far enough ahead so that, by the time you figured out what block you wanted, it hasn't rotated past you. Okay. And the other problem, of course, is this is a little bit unreliable because if you lose one block, you're toast, okay, because all the rest of the file is gone. Okay. And random access, really bad, right? Because the only way to random access is to walk your way all the way through to the point of interest. So effectively, random access is like sequential access up to the point that you want. Okay, so that's pretty bad. You'd be better off reading the whole file into memory, well, that's today, and finding your spot than you would actually trying to pull it off the disk randomly. This was actually used in the original Alto. And does anybody remember why they know the Alto? I told you about the Alto earlier in this class. Yes. Yeah, this was the first PC with mice and windows. Okay? So, and by the way, they didn't even bother trying to allocate contiguous blocks. Okay? It's sort of what you saw is what you got. Now, there is a different type of linked list we could do that's still kind of common. Does anybody know what that is? Go ahead, yeah? Yeah, the FAT32, right? So here, this is similar but not quite the same. So there's this thing called the FAT table or file access table. All right? And what's in this table is not data, but actually pointers to data. Okay? And so what does a file look like? Well, a file has a starting block ID, like say 217. We go to point 217, and that in the FAT table, we say, oh, the next block is 618, and then the next block is 339, and so on until we hit a null pointer. And so I can figure out, I can walk the linked list not by reading the data, but by just looking into the FAT table. Okay, so you could think of it another way. You could say I took all of these pointers and I collapsed them together into a table that was the FAT table, and as a result, I can basically walk the linked list without reading everything. Is everybody with me on that? Okay. And, that's not too bad. It works. And surprisingly, it was so popular that it's still in use. So if you have a USB key or something or a camera, it may actually be formatted as FAT32, which is the final version where these pointers are 32 bits in size. Okay. So sequential access is kind of expensive, and random access is also expensive unless, of course, you cache this in memory, and then you can very quickly figure out which blocks you need, and you could actually rearrange them and do good head movement and so on if you wanted to, because you can just look through the FAT table. Yes, question?
Is this table only stored in one location?
So this is stored on disk. Usually there's a couple of duplicates of it because it's so important. And oftentimes, certainly today, the FAT table is entirely loaded into memory before you use it. That wasn't always the case when memory was small, but now pretty much they do. Question? Yes?
So when you want to read like a sequential file, would you just kind of, as a precursor buffer, find out all the sectors you need, and then read that into your disk?
So you could, yeah. So I was suggesting as an optimization, you could walk first, read later. But oftentimes they don't do that, especially if this particular file system is on Flash or something, then there really isn't a huge advantage to doing that. OK. Any questions? So this is a file system you use. And notice, by the way, I've been a little bit elusive up here about, well, what's a directory entry? Well, a directory is a file. And that file has a series of names followed by starting positions in the FAT table. And so basically, you have to have a pointer to the root file. So that's sort of, there is a first file, which is the first directory, and then everything follows from there. OK? So now, here is another option. So the problem with this linking is literally to do random access, we still have to do a lot of walking. So there is no offsets that we can do. There's another option here, which is linked access or index allocation. And here, what we're going to do is we're actually take some blocks, a disk block, and count that disk block not for data, but as an index. So here, a directory entry has a pointer to the index block, which is 19, and then the index block has a series of pointers, 9, 16, 1, 10, 25, that point to which blocks are successively in the file. Okay, so this basically says that the first block is 9, the second is 16, the third is 1, the fourth is 10, and so on. Okay? Now, in order to do random access, we make sure to load this whole block, and then we can compute offsets easily, and then we can figure out we really need block 10, and we can go get block 10. Okay? Questions? Yes? So if you lose the index block, you probably lose the file. Yes? Okay? This, by the way, this kind of file system was actually used in the VAX, the VMS file system. And And also, it was used in nachos when we made you do file system. There was a project at one point. Yes?
So, like, does this limit file size or something?
Yeah, good question. So what limits the file size here? The maximum number of blocks you can have in your header block. That's good point. Okay. Now, you can have several, you could link these blocks together as well so that you could have successive index blocks. Okay. And the user is kind of pre-declaring their max file size in the actual VMS, which is how many header blocks they're allowed. So the pros here is we can easily grow up to the space allocated for the index. Random access is fast, assuming you can load the whole index into memory. Cons, it's very clumsy to grow the file beyond a certain point, which is this index size. And there's still a lot of seeks because you may actually have to pull these blocks in from all over the disk. So notice that there's nothing in here that says that these blocks are close to each other. Right? It just says there are blocks pointed at. Yes, question?
For all of these file systems where we keep talking about the fact that we're not guaranteed they're close, why would operating systems just say, well, best effort? Like, we're fine, no guarantees. It seems like that'd be good enough.
Yeah, so the question is, why doesn't the operating system just say best effort? So that's a good point, and I think the right answer to that is originally they didn't, and ultimately they did. So what do I mean by that? Well, when you say best effort, what you're really saying is I'm actually going to try to do some work to make sure that I'm mostly accessing things that are close to each other. And so that's actually a set of heuristics. Okay, and if you notice, we started out when we had the continuous allocation where we forced our allocation was constrained to be close to each other. That was the only thing allowed. All of these other ones now have locality as a potential optimization, which is kind of nice. It's no longer a correctness feature. It's something I can put algorithmic work into making it happen most of the time and be pretty happy. And that's exactly the answer that's going to come up in a moment. But I just want everybody to see that there's nothing in this structure that says that these blocks are close to each other. We have to do something else. Okay. So that leads us to, remember BSD, Berkeley Standard Distribution of Unix? Well, BSD had a multi-level indexed file which is pretty much used to this day. Now, it's going to look complicated, but there's a good reason for it. Okay, and it looks like this. So it's efficient for small files, but still allows big files. So why do we want efficiency for small files? Because, at least in Unix, with the data they had, there's a lot of small files. Why do we want big files? They exist. Okay? So, and if we can't handle big files, there's a significant market that we lose. All right. So, file header contains 13 pointers. Okay? Hope none of you are superstitious, because we're going to use 13 for a little while here. So, fixed size table. So, remember here, a fixed size table kind of limited us in how big our file could be because we couldn't have any more blocks than fit in here. But we're going to be a little clever about these 13 pointers. Okay? And we're also going to introduce some terminology which pretty much is stuck, which is the inode. So that's just the header for describing the file. And here we go. The first 10 pointers directly point at data blocks. Block 11 points to an indirect block, okay, which is a pointer to a block of pointers. Block 12 points to a doubly indirect block, which is a pointer to a block of pointers to a block of blocks of pointers. Block 13 points to a, you ready for this? A block of pointers which point at blocks of pointers which point at blocks of pointers. Okay. Now, discussion. So what the heck is this all about? Why would we do something like this? Somebody explain this to me? Yeah. So small files work pretty easily. Why? Yeah, so assuming that the small files fit in 10 blocks, we can easily find data in them just by going to the first 10 pointers. So that works great. And by the way, at this time in Unix history, blocks were 1K in size. So we're really saying for files under 10K, we're good to go. Okay, today they're more like 4K. But anyway, okay, so now where do the big files come into play? Yeah. Yeah, so what happens here is successively more and more blocks can be pointed at. Okay, and we'll show you an example in a moment. But basically, if you have 1K blocks, this thing here basically allows file sizes up to 16 gigabytes, which, by the way, was bigger than anybody in the world could possibly imagine a file needing to be. Okay? Now, unfortunately, pictures that one takes on vacation trips are 16 gigabytes with new cameras, right? Maybe not quite, but it's getting pretty close. So the fallacy, of course, is that you've got things like the Earth, what is this? The Earth EOS is basically the system that's taking pictures of the Earth continuously from satellites. Is basically at least 2 terabytes or more a day easily of data. All right, so this sort of fallacy of 16 gigabytes is no longer there, but they were doing well for their time. So pointers get filled dynamically. You basically need to allocate an indirect block only when the file grows beyond 10 blocks. And on small files, there's no indirection. So it's actually a pretty efficient for small files, but it handles the, and I say big in quotes, files well. Okay? And all we need to do to handle modern formats is we can do things like make the block size 4K and then put an extra indirect, a quadruply indirect pointer in here, and we pretty easily make for very large files. Question? Yes?
So is there a huge disconnect or speed between like a 10K size file and an 11K?
So the difference between a 10 and an 11K file is basically that 11th K you have to get at with 2 reads instead of 1. But once you've loaded this indirect block into memory, then subsequent accesses to that 11th block is not going to be too bad. So it's more about, if you do good caching in memory, you're pretty good. So here's an example. So by the way, the inode, of course, has a whole bunch of stuff in it. It's got like the mode, things read, write, execute for various things. It might have who owns it, what some timestamps are. And then here the direct blocks are pointing at actual data. The single indirect block points at a block, which points at data. And then doubly indirect, and so on. Okay, does everybody get the picture? Okay. And why, by the way, do I say that one of these indirect blocks points at 256 other blocks? Yeah.
block is 1K?
Yep. Block is 1K.
Yeah, block is 1K. And then each pointer is about 4 long bits.
Yeah. 1K blocks, 4-byte pointers, 256 of them. This sounds a lot like virtual memory, right? Only this is the file system. So how many accesses does it take to block 23? Well, 2, because you're going to actually execute the single indirect block, or you're going to have to load the indirect block here first and then the data. How about block number 5? Only 1, because once you've got the inode, you just get the data. Block 340, you actually have to go to the double indirect block, an indirect block, and then the data. Okay, and so you should be able to figure this out if you were forced to. Yes?
Does Cost try to do any thing with like stacking the indirect blocks close to down the same track? Since you basically will never need the double indirect without the indirect.
Yeah, so at the time of 4.1 BSD, they didn't really try to do any locality optimizations. We'll talk about 4.2 after the administrivia. Okay, pros. Simple, more or less, right? Files can easily expand up to a point. Small files are very cheap. Whoops. Cons, lots of seeks. Why? Well, because potentially this data may not be close to each other, and so maybe you don't actually have very efficient access. Okay? Any questions? Now notice, by the way, when we talk about inodes, there's a lot of other stuff in here, and that's typical. So all the things you think of as associated with files are really part of the inode in addition to what blocks are associated with it. Okay. All right, so the votes are in. If I had my envelope here, I could open it, although this is New Times, New Tech, Transforming the Future. Okay. So, results of the poll. Yipes. Now, this is the point at which one might demand a recount, but we're not. Okay, I think, the problem is I was getting very passionate email on both sides of the issue. I figure this is hard data. I trust my TAs to count correctly. Those of you who didn't come to section or who abstained, I didn't actually get abstains from everybody. Didn't get your chance to vote, I guess. And so we're going to go with no midterm. Now, this is obviously very close, but for those of you who didn't get to take another midterm, let me say the following. The last midterm was only 20%. If we take another midterm, what will happen is the last midterm will become 15%. So you will have shaved 5% off of the grade and gained a midterm 2 weeks before the final. So I don't know if that makes you feel any better or not, but for those of you that are very concerned about this still and your grade, come talk to me. I think the fact that it's only 20% is 20%. I think the best arguments that I heard included things like, well, you told us what the distribution was at the beginning of the term, and I agree with that. So I didn't really want to change things out from under people. So anyway, so I took the midterm off of the lecture schedule. And I apologize to those who really, really wanted a midterm. I'd be happy to print out one of the ones I've got on the website and let you watch you take it. I won't give you any points for it, but you're welcome to take it. Okay. I'm assuming you'll do that in preparation for the final. So, all right. I know that there's half of the class is unhappy, but I apologize. I tried to make sure this was... Okay. I said this last time. I want to say it again. We're in that point in the term where people are getting nervous and they're getting into Project 3 and they really want things done. But keep in mind that this is a zero-sum game. So make sure that you're participating. Everybody should be participating in the group. Normally, the points get distributed directly to everybody the same way, but under extreme circumstances, we will do otherwise. So if you're having problems in your group, make sure your TAs know about them. If you're feeling left out and people don't appreciate you, come talk to me. If you feel like there's somebody who isn't appreciating the rest of the group, come talk to me. Let's know, okay? This is something where I want to make sure everybody is working together. Okay. And I'm more than happy to have meetings with the whole group in my office. I do that multiple times a term, so that's okay. It's not a big deal. Also, make sure to do your project evaluations. I think we've been hitting on people enough about this term that it's been good. But if there are evaluations you're missing, and you should be up to Project 2 now, make sure that they're in. Okay. Now, the any questions on Administrivia? So you can breathe. Yes, go ahead.
Is there a way to check if you've done the evals?
If you're not sure whether you've done them, ask your TA. It turns out we don't have an interface for knowing whether you've done them or not. It's an obvious thing that ought to be there, but it just isn't. We're dealing with scripts from 1923. They're written in COBOL. No, you guys don't even know what COBOL is. So Angela wanted me to remind people that if you have any regrade requests for midterm 2, you got to get them to your TA, or you could get them to Angela, since she's sitting in front here, and I don't see the other TAs right now. Oh, there they are. There's Christos. Yeah, get them to your TA. If you have regrade requests on Project 2, make sure those are in within a week. Okay, because our reader is, we have one reader for this whole class, and so he's would be overstressed if he's got to deal with Project 2 at the end of the term. So, okay, are we good? All right, no midterm. I took it off the schedule. We'll talk about security instead. Okay. So, let's switch gears a little bit on file system. So what we've been doing up till now is we've been saying, let's get a more and more intricate file system structure to allow combined support of small files, and big files. A different tack is we care only about performance. How could we deal with that? Now, our first stab at truly caring about performance was, let's force continuous block allocation. Now, the problem with that was fragmentation really got us in trouble. So a different approach is exactly what the Cray 1 did. And Cray was known for speed. And there was a file system they had called Demos. And it looked like this. Okay, a file header, rather than a single base size group, was up to 10 of them. And notice what this does. So this is kind of like the first file system I showed you, where you say, here's the base of a chunk, and here's its length. And the idea is that those sectors are a continuous chunk of sectors. And then we can also have up to 10 of these base size chunks. Okay? And that would give us kind of an attempt at the best of both worlds, because we can handle larger files even when there's fragmentation, while at the same time making sure that we mostly have continuous allocation here. Yes?
With disk sitting so big today, are we kind of seeing a return to like continuous blocks?
So, larger file systems have larger disks have caused a whole series of problems over time, because not the least of which the pointers that people talk about, 32 bits are just not enough. And so there's been a lot of evolution to bigger bit widths, like 64 bits. Not so much of a return to this, okay? Because Linux is more based on kind of the BSD form, which I just showed you, and we'll get back to it in a moment. So this one has not resurged too much, but this was kind of a nice file system. It's kind of like, it's basically like segmentation, okay? Now, what we're doing is we're reducing disk seeks by making sure that every file chunk is contiguous here. So this is kind of a stab at performance. And the downside, it is kind of interesting, by the way, that even in the Cray 1 days with a 12 nanosecond cycle time, which is incredibly slow by today's standards, it was still about a few millisecond or a few million instructions per seek. So that number I gave you at the beginning of the term has been constant pretty much over time, which is kind of amusing. So basically, they were trying to get rid of seeks as much as possible because they're so expensive. And so the header was a table of these base size pairs, 10 block group pieces. Sequential reads are fast as long as you're in here. How do you do random access? So sequential is pretty clear. How do you do random access here? Yeah. Yeah, exactly. You kind of walk this, you pull these 10 pointers in and you add the sizes up till you get to where you want, and then you just did an offset on that, right? Yeah, exactly. So it's efficient at random access as well. What's the unfortunate thing about this format? And think what happens is the disk gets really full. Yeah.
Well, as this gets really full and you have less and less contiguous spaces to block, you simply can't deal with big files.
Yeah. Notice that the size of the file that this can deal with depends drastically on how fragmented the disk is. Because these chunks here, they can only be as big as the biggest contiguous chunk you find, and therefore if you can only have 10 chunks and they're all small, you got small files. Okay, so this particular structure sort of really falls apart when things get fragmented in full. Everybody with me on that? Now, so how do you find an available block group? Well, this is, again, one of those situations where you have a huge bitmap and you're just looking for groups of free blocks. Okay, so how can we fix this fragmentation problem? Yeah. Okay, so we could make sure that all chunks are the same size. All right, now, yeah, that worked for us in virtual memory, right? The problem, of course, with that is what size you're going to pick, and what you'd really like is, gee, my ideal situation is a file fits on a whole track if I can do it. But yeah, we could force all the chunks to be the same size, and that would give us a maximum file size. What else could we do? Yeah.
Make sure chunks are multiples of powers of cube.
Yeah, so we could start pulling tricks like malloc and so on, where we have powers of 2 in sizes, and that might give us a better job of finding the chunks we want. Yeah. Okay. Well, one thing we could do is we could put indirect blocks back into this. Okay, and here's the large file version of Demos, where a file header has a base and size pointing to an indirect block, which has a base and size pointing and so on. Okay, so the indirect block group actually has a whole series of pointers. Okay, so we have pointer to a bunch of pointers to a bunch of chunks. So the nice thing about this structure is we still have a lot of growing space even when our chunks are fragmented. So if worse comes to worse, this performs badly because we have lots of little chunks, but at least we can get bigger files out of it. Okay? You know, and so you can actually do a calculation, 1,000 blocks in a block group. You maybe get an 80 gigabyte maximum file. Okay, and whoo, that's huge, right? Well, again, we're talking a couple of decades ago, right? 3. So what about this scheme? So on the one hand, very fast sequential access. Free areas kind of merge simply by, you know, when you free up groups of blocks and they happen to be next to each other, suddenly you got a big chunk, okay? It's easy to find free block groups when the disk is not full. When the disk is full, this starts getting very problematic. So disk full means no long chunks of blocks, you got fragmentation, and you've got a continuing problem. So what do you think Demos did? So what's the biggest thing that gets in the way here of finding large chunks? What could you do to this disk to make sure that there were large chunks on it? Yeah. So you could defragment it, but suppose we're not willing to spend that cost. What else could we do? Okay. Maybe. So what if you put in a brand new disk in there? Is there any fragmentation? No? What if it's, are there large chunks? Yeah. So what is it about an empty disk that's different from a full disk? Yes? The empty disk is empty, right? Okay. So basically, you know, in the case of a full disk, you kind of got the worst of BSD with lots of seeks and the worst of contiguous allocation, so you got to recompact and so on. And so the answer is you don't let the disk get full. Okay? And in many systems, you say, well, the disks are always full. But what full really means is the disks are as full as the file system is going to let you go. Okay? So what you're not aware of is most file systems have a limit of how full they allow the user to get, and that's maybe 10% below the maximum. And that 10% number is a pretty good number for making sure that there are large enough chunks to get good performance on a wide range of different types of files. Okay? So, you know, why are disks always full? Well, everybody needs data. How many of you have run out of data of space recently? Okay? Have you run out of space on your project file system? I don't think we've had too much of that recently. That always happens. If you've run out of space on your personal computer, maybe? Okay? Not as much, right? Well, one way you fix running out of space is you announce to everybody, we don't have enough space, delete some files. I'll tell you, that never works. Okay? Nobody ever frees up space when asked to. Okay? Another thing to note is that as disks keep getting bigger, maybe the fact is we don't really need to worry about full space because the world's set of disks is bigger than what anybody needs. Okay, so maybe we never have full disks. Now, it's one thing that is kind of interesting is every new how many people have put a new disk on an old system? Anybody? Okay, and what did you do with the data you had on the old system? Copied it over. And was there space left? Yeah. So what you find is that new disks are often like a factor of 4 bigger than the old ones, and so there's plenty of space, right? So anyway, so maybe full disks are just not an issue, but the solution is you just never let the disks get full, okay? And that's exactly what happens under the covers. And when you make a new file system, you can often set this parameter, but it's usually defaults to about 10%. Okay? So you're basically trading a little bit more for disk, and you're getting good continuous allocation and much better performance, and it's worthwhile. All right. Questions? Now, just before we break, I want to talk about BSD 4.2. So 4.2 is the Uber release of BSD. This is the one that had sockets in it that everybody loved, and so on and so forth. This was also the one that had the fast file system optimizations. And what they did was basically, they took the same file header structure, 13 pointers, and what they did instead is they actually incorporated a bunch of ideas to try to guarantee that the operating system would do its best job possible to give you contiguous allocation. Okay? So it uses a bitmap allocation instead of a free list, so it knows what blocks are next to each other. It tries to allocate files with contiguous space. It reserves 10% of the disk space. And it does skip sector positioning, which I'll tell you about in a second, all to try to get the performance up. Now, what's interesting about this file system is they didn't change anything about the structure of the inode. So the inode was identical. All they did was they put algorithms on top to try to get the blocks to be close to each other. That's all. Okay? So, you know, for instance, problem, when you create a file, don't know how big it is. Okay, what do? How much allocation do you do for the file? Right? Because remember, open, write, close. So you never know how big the file is until the very end. So what did they do? Well, in Demos, they actually use power of 2 growth. So once it grows past a megabyte, you get 2 megabytes and so on. In BSD 4.2, they just found a range of free blocks somewhere in the middle of everything, and they kind of grew the file there. So each new file kind of staked out space on the disk that was free. Okay? And to expand a file, you just first try blocks close, and then you go find another area to stake out. Okay? And this worked pretty well. Another thing that they did in 4.2 BSD is they stored files from the same directory near each other. Okay, why might you want to do that? Well, typically, say you're compiling something, you're going to open every file in the directory. Wouldn't it be nice if you didn't have to move the disk head at all? So they would allocate the directory and the files all together on the same tracks. Okay, and this led to what was called the fast file system, which I would say is the old file system with a whole bunch of heuristics to try to get blocks close to each other. And there's actually a paper up by McCusick that I put up for reading that talks about what they did on the fast file system. So if you take a look on the lecture page, you can actually see a bunch of those optimizations. Yes?
So you might be able to read what's right above the operating system to do all this advanced stuff. The hard drives have taken that.
Yes. So the question is, didn't we learn last time that because of logical block addressing, exact knowledge about what's close to what is kind of hidden from the operating system? That's true, but the attempt is still made so that the logical block addresses that are close to each other are close to each other on the disk. And so there's still some benefit to doing, well, there's a lot of benefit to doing this kind of optimization. Good question. Okay, and I don't know if anybody got the optional 4.3 BSD book that or had access to it that was on the website. There actually is a whole bunch of interesting stuff about the file system in there. I'll put up some reading on that too if anybody's got access to it. Okay, questions? Okay, so let's take a break and we'll come back and we'll talk a little bit about rotational delay. So let's finish up here. So I mentioned this briefly, but this was one of the another thing that they addressed in 4.2 BSD, which this notion that even when you're really good about placing your blocks on the disk, you'd often end up slow in reading back. And it was like, why is that? Well, because you'd pull the first block off, and by the time you figured out which block you needed, the disk had rotated past the second block. Okay? And so what happened? Well, they actually developed this thing they called skip sector positioning, where literally what they did was rather than putting consecutive blocks of the file next to each other on the disk, they would skip several sectors as a way of dealing with this timing issue. So that by putting, think of all the pink ones here as being part of the file, you pull the first one off, and by the time you knew what you needed for the second one, you hadn't missed the second one, and so on. And so by spreading the blocks out, they were able to get much faster read access. It seems kind of obvious in retrospect, but it certainly wasn't at the time. So this was another optimization in the fast file system. Question? Yeah?
Why is that necessary given the Inode structure? It seems like you always know in advance pretty much.
Well, the real answer here is that suppose you're reading from a file. So the typical structure is you go into the operating, or you do a read system call, you go to the operating system, it pulls block off the disk, it returns the data to you, you make another read system call, so you're kind of pulling the blocks off the disk. And by the time you kind of go back and forth in that path, then it's passed you by. And so because the operating system doesn't know you want to pull the whole file into memory, in fact, it probably at that time couldn't even deal with it because the memories weren't big enough. So it was basically feeding data off the disk into the application.
Wouldn't it make sense to pull 5 or 6 blocks from each file at a time?
Yeah, it might. But apparently the access patterns that they often saw didn't do that. And so this was a way of optimizing things. Yeah?
The multi-programming system, like after you do a read, chances are someone else will go in and do their read, right?
Yep.
Doesn't that mean that S deviates from where you are in the sector in the track, so it doesn't really matter?
Well, you have to be careful in a multi-programmed environment, and that's where things like the elevator algorithm and so on would come into play. So assuming that even if there's 2 people making requests, that there's enough requests a little bit ahead of the game. But yeah, you're right. You could get into an access pattern where there was nothing you could do here that would matter. Now, of course, this is not as necessary today because smart disks actually have track sectors. Okay? But another solution which was brought up actually up there is, well, we could go ahead and read a bunch of blocks. And that was another thing that they did as well. They had that optimization. But the real answer today is there's enough memory on the disk that when you go to ask for a block, it reads the whole track and puts it into RAM and disk. And then it doesn't matter how long it takes for you to ask for the next block because it's now in the track buffer and it's much faster. Okay? And so if you go to buy disks and you take a look, you'll see that they actually have a certain amount of memory that's as spec'd as part of the disk. So 32 gigabytes is a standard amount now, or 16 32 gigabytes is pretty standard on the big disks. Question? Yes?
16 or 32 megabytes?
Yeah, I mean, sorry, megabytes, yes. Sorry, my brain is a little fried today, yes. It's still quite large relative to the track. Okay. Now, thanks for that correction there. Yeah, megabytes. So, as I mentioned, track buffers, elevator algorithms, bad block filtering, all that stuff's done on the disk these days. So, pretty smart disks. Okay. So let's, unless there's any other questions on this, let's actually change a little bit. We're going to stay with file systems for a moment, but we're going to switch topics slightly. Yeah, question? So NTFS has a lot of similarities with BSD. It's a little different, and actually, that's a good point. I should really put together a structure for NTFS one of these days. Maybe I'll do that. Question? Yes.
What does journaling mean?
I'll talk about journaling in a moment. Actually, we'll get to that, I think, or if we don't, we'll talk about it next time. Promise. So, how do we actually access files? So. Well, all the information you need about a file is in the inode. So assuming you can load the inode, then you've got all the information you need to figure out where your blocks are. So how do you find the inode? Well, that's a little tricky, right? Because an inode, is pretty, it's not very useful from a piece of information standpoint. It's got a few pointers in it, right? So how do you actually find out which inode you need for which file? Okay. Directory structure, okay, you need some sort of naming. Okay, so one option would be for the user to know what inode is. Well, open inode 14553344. Okay, that might work. Probably wouldn't be very popular, right? Another option is a little better, which is you want to have some way of actually mapping names to iNumbers or inode numbers, and this is kind of what we call naming. Of course, another option would be icons. So, how many of you have switched most of your file access to clicking these days? Anybody? Or are you still actually walking your way through directories? CD and LS are your friend. Okay, good. This is, of course, how icons are kind of where Apple made their money. But let's talk a little bit about this particular naming scheme here, which is a little more interesting. But in general, naming is this notion, it's the process by which the system translates human-readable names into some system resource. And in the case of files, we need to translate from strings or icons to iNumbers or inodes. Now, what's the difference between an iNumber and an inode? Typically, the inodes are allocated in chunks on tracks, and an iNumber sort of says which inode starting from the beginning. Okay, so inode 1 is the first inode, inode 2, inode 3, inode 4. Okay. So interestingly enough, naming is pretty general. So you could imagine files, if you have a global peer-to-peer file system or a cloud storage system, that when you actually have a name for something, it could be anywhere. It could be in China, on some server somewhere. Okay, and that's very general naming. And we'll actually talk a bit about this a little later in the course, but for now, let's stick to much simpler naming. So we want to turn names that are local into local files. Okay, let's keep the problem simple for a second. So, of course, the directory is the thing that you're all familiar with. And this is basically just a relation for mapping names to inode numbers. Okay, and how do you construct a directory? What is a directory? It's a file, right? So a directory is just a file. Why? Well, because that's a good existing mechanism. And so basically it's just a file full of file name iNumber pairs. Okay? And, all right, so how do you find the directory? Yes?
Well, you could store like the root directory and then like kind of cache where you currently are, and then like so the root directory will point to a bunch of other directories, and then like
Exactly. Yeah, so we need to have some directory, which we call often the root directory, which is the top one. And then once you got the root directory, then you look up the file name iNumber of the first of your path, and that points you to another file, which then you look up the next name, and so on until you eventually get to the file you're looking for. So directories are just files, all right? And it needs to be quickly searchable. So, just like any other thing, you can build this in multiple ways. So you could either have a simple list where you just list the file name iNumbers in the order they were created, or you could build a hash table, or you could build a database. Okay, now the original Unix systems actually were just plain a list. And the problem with a list, of course, is that the files are in whatever order things were created. So it wasn't a very efficient searchable mechanism. Things have gotten a little better now. Some operating systems actually use hash tables or something like that. So how do you modify a directory? Well, if you were to actually look at the list of system calls that Unix supports, there are things called make dir and remove dir, okay, which then become actual commands. And they're part of how to modify these special files, which are directories. Okay, so that's not particularly magical. They also get modified automatically. When you say open a file and you give a directory path, it automatically finds the directory and puts a new entry for you. Okay, so that's a transparent way of modifying the directory. You probably haven't thought of it that way, but certainly when you create a new file, you got to enter an entry into a directory. Yes, question?
Why were there dedicated system calls made for creating?
Well, because if you want to actually make, so because directories are kind of special files, they're sort of marked as special files, and there are special commands for reading and writing entries into them in sort of the original way of doing things. And so these extra system calls were for creating those special new files. It's a different file type from a regular file type. Now, you might say, well, that didn't really answer the question. Well, I think it's basically these files are marked in the inode in a special way that there's certain types of manipulations you can do on them that you can't do with regular files, so for whatever that's worth. Because what they're storing is actual inode numbers, and so it's sort of different information from raw bytes. I don't know if I have a great answer other than what I just gave you there. So directory organization. So directories are hierarchical today. Everybody's used to cd/foo/bar/baz/file. That actually wasn't always there. So I actually had to deal with some IBM systems that everything was flat. So it was basically you got a partition that was mounted and all the files appeared in a flat directory space. Imagine how painful that is to deal with, okay? Huh? Unless you can search, but that actually wasn't in the cards until much later. So yeah, this was pretty painful. The only redeeming quality, I guess, was there weren't very many files, and so it was easy to find things. I don't know. But hierarchy today, how do you deal with things? Well, it's very simple. So files are an ordered set, /program/p/list. And here's a directory structure. This is right out of your book. And if you notice here, we have a root directory, which has names that point at other directories, which have pointers to other directories, and ultimately have pointers to files. Okay, and it's not really a hierarchy, because if you notice, this has actually got loops in it. Okay, so you can actually create loops in your directory structure if you want. Anybody ever created a loop in a directory structure by either design or by accident? Yeah. Okay. Many systems allow your directory structure to be organized as a graph, and this shouldn't surprise people too much. There are a couple of things I did want to mention. So there's this idea of a hard link versus a soft link. Does anybody understand the difference between hard and soft links? Yeah, go ahead.
A hard link is the file system actually knows it as a separate file, like it thinks it's a separate file.
Right.
But a soft link is a special type of file.
Yeah. So a hard link is actually what you see here. See how I see the file TC is pointing at a file? This is actually a hard link. Because if you look in the directory structure, there is, there's the name, and next to it is the inode. A soft link is actually a separate file that says, well, you think you're at this file, but it's really this other file. And all that's in this special, if this were a soft link, and I don't have an actual soft link here, but if you had a soft link, the file would actually be /foo/bar/baz marked as a soft link. And so then when you do here, you cd into Jim, and then you cd into mail, and then it's /foo/bar/baz, you cd into that, it actually takes you to some completely different place in the file system. And so it's not a real link in the sense of a link to an inode. It's actually just the name of a file in the file itself. Okay, so a soft link is a type of file, whereas a hard link is actually in the directory as a link pointer to an inode. Yes?
Are links have to be linking to files on the same drive because they use
Yes. So that's a good point. So the hard links often pretty much all the, yes. We'll say that hard links always have to point to things in the same drive or partition. Yes. Question? Yes.
If I delete a hard link and then another hard link pointing to the same file, what happens?
So that's the other kind of interesting thing about hard links. You can have two hard links in completely different parts of the file system pointing at the same file, and it automatically does reference counting. So if you remove one hard link, then the other one is still there. Whereas that's not true with a soft link. A soft link is just, here's a name. So If you delete the file out from under it, nobody ever notices, and you can actually try to CD into a soft link, and it'll say, sorry, no file there. Question? Yes?
Is the benefit of a hard link just the fact that you don't have these broken references, or what other benefits?
Yeah, hard links are a little bit less flexible than soft links. They're a little easier. They can point outside of the file system and so on, whereas hard links are really much more limited to being within the given file system. And they don't transfer well either, so usually people use soft links in big directory structures just because it's easier for things like tar and so on to grab the soft links. Another question? Yes? Say again? You can absolutely have a hard link to a directory. Yes, so you can actually have two different directories. Well, here's a good example. See? Here's two links to the same directory. So this would be two hard links to that same directory. So it's possible, yes. And by the way, the link command, I know these are little details, but what the heck, it's the end of the day. ln is the link command, and if you, depending on whether you put a -s or not, gives you a hard link or a soft link. So you could play with it if you want. Okay. So name resolution is the process of resolving names. Ooh, isn't that deep? Now, notice, what do I mean by name resolution? Well, if I'm trying to get to this file, and I know that the name is /gim/hype/hex, then name resolution is the process of taking that string /gim/hyp/hex and turning it into this inode. I'm resolving the name into an inode so that then I can open the file. Okay, and as you can see, because this is the typical directory structure that everybody has, I actually have to open the root directory, then open this directory, then open that directory before I open the file. There's actually a lot of work involved in name resolution. Okay? Now, that's why the more elements you have in your path, the more work has to be done. How can I reuse work for name resolution? Caching. Oh, yeah, everything's a cache, right? So, yes, indeed, there is a name resolution cache in the OS. And the tricky part about that is making sure that that name resolution cache knows when something that it thinks is cached has changed out from underneath. So you have to keep that cache consistent with the structure that it's referencing. OK. So a dumb example, but how many disk accesses to resolve /my/book/count? Well, first you read the file header for the root. That's a fixed spot in the disk. You read in the first data block for root. You start searching until you find /my. Then you read in the file header for my off of that first file. You open up my. You read the first data block for my. Search for book. Read in the file header for book. First data block of book. Search for count. Finally, you read the file header for the file count, and you can actually open it, and you're good to go. So there's a lot of disk accesses. Okay? Now, if this makes perfect sense to everybody, imagine for a moment that this name resolution process actually was resolving file names that were global somewhere. It could be in China, right? It's possible that every file I'm opening actually has to go to some different place around the net to resolve. Okay, so when we talk a little bit about distributed systems in a week or so, we're going to have to figure out how to maybe optimize that process if we really have to do global name resolution. All right. So, of course, there's the notion of the current working directory. You're all familiar with that. What is that? Well, that's a per process pointer to which directory is the current working directory. And if you open a file without the slash at the beginning, the assumption is use the current working directory as your starting point for any further name resolution. OK. Good. Questions? All right. So where are the inodes stored? Well, in early Unix and the FAT file system, headers are basically in a special array in the outermost cylinders. OK, this has the positive effect that I guess the outermost cylinders are the fastest ones, the highest bandwidth. It's got a lot of negatives. What are some good examples of negatives for this structure? Yes? Yeah, if your file's on the inside of the disk, you're going back and forth to grab the inode and then go to get the file. So there's a lot of head movement. This has also got another series. Go ahead. If you got a head crash and it takes out your outer cylinder, you just lost all of your data, the whole disk. Okay, why is that? Because the only information about what's on the disk was just toasted. Okay, so that's kind of this seems like a bad arrangement from a durability standpoint, right? So, the header's not stored near the data block. Small files require a seek. Boy, that sounds bad. There's a fixed size typically, and so this was a little bit of a problem that you could actually run out of inodes because you have more files because all your files are small, so you have more files than inodes, and then basically your disk is full. Doesn't matter that there's more space in the disk, there's just not enough inodes. Okay? So later versions of Unix and most modern file systems are a little more clever about this. So for instance, inode for a file is often stored in the same cylinder group as the parent directory. So what's a cylinder group? Well, you know what a cylinder is, right? That's all the tracks that are you get without moving the head. A cylinder group would be a group of tracks that are close to each other. That's a cylinder group. And so what we do is we make sure that there are inodes spread throughout the whole disk, and you allocate an inode from the cylinder group that's got the file or the directory or whatever. And as a result, there's not a lot of head movement. Once you go to the directory, then the inodes of all the files in that directory are close by, as are the files. Okay, so that's great from a performance standpoint, and it's great from a what happens with a head crash standpoint, because somebody who knows how to reconstruct a disk, and there's actually a lot of software for this, or there's companies that'll charge you $1 zillion to get your data back, they can find the inodes that aren't damaged yet and reconstruct much of your disk in that case. Okay, so a head crash is not the end of the world. Yes?
Is the cylinder thing by doing an ls of a directory containing a large number of files so slow, or is that a different factor?
The problem with ls is for a large directory is often because the directory isn't sorted, and so it's got to load things in and sort them, and then then it's got to go to each individual inode and find out what the values are. So even if they were close together, there's a lot it's doing. Because when you think about ls, it's doing a lot more than just telling you what's in the directory. It's actually finding out what all the file permissions are and all the information about each file. And I suspect it still does that even when you don't tell it to print it out. That was your next question, I bet. So the pros of this are, so basically Unix BSD put a portion of the file header array on every cylinder. So this was another fast file system thing. Small directories, you can fit all the data, file headers, et cetera, on the same cylinder. So you can get the whole directory and all the files without moving the heads. Okay, and so I think that's good. So reliability, I said that as well, and this was all part of the fast file system. Okay, I think we're at a good stopping part here. So in conclusion, we'll pick up next time. We talked about multi-level index schemes like 4.1 BSD. Inode contains file info, direct pointers to blocks, etc., indirect blocks, doubly, triply indirect blocks. We talked about Cray Demos, which was an attempt to go after sequential access. Was a little bit subject to fragmentation. We talked about 4.2 BSD, which was a nice file system plus a set of optimizations. Okay, we talked about naming, which is the act of turning user-visible names to actual resources. And next time, we'll actually start talking about availability, durability, reliability, and for the person who asked about journaling, that is in that category. So we'll catch that up next time.